For my reinforcement learning project, I decided to build a reinforcement learning environment called Runaway and find an optimal solution to the environment using Q-Learning. Quick outline of the presentation. I will first go over the Runaway environment that I built, including the actions that you can take, rewards, state, and the goal of the game. Then I'll give a brief overview of Q-Learning, followed by how I use Q-Learning to learn an optimal Runaway strategy. And finally, I will talk about the future directions of this project to conclude the presentation. So let's jump into it. So the Runaway environment is a game in which the agent plays as a green slime and is chased by an evil eye minion. The player has to avoid the minion for at least 1,000 time steps in order to win. The agent has the upper hand though. It's faster than the minion, however, the minion is persistent and the game board is small, being only 500 pixels squared. So avoiding the minion can prove a difficult task. The actions that the agent can take are up, down, left, right, or it can halt, meaning it can just stay where it is or do nothing. The state of the game is represented as a vector of 4 numbers, the x and y coordinates of the player, and the x and y coordinates of the minion. A single reward is given for every time step the user survives. 1,000 extra rewards are given if the user wins or survives all 1,000 of the time steps. And a negative 100 rewards is awarded to the user if it's captured. So let's go ahead and do a live demo. All right, to do a live demo or to try this out yourself, I've created a little command line tool that will start up the applet or the game and let you start running it. So once you've downloaded the repo from GitHub, all you need to do is make sure you follow the instructions of the README to install all the dependencies, and then go to the command line inside your repo and type python play.py and then hit enter. And this will pull up the game. And so you can see you can control the minion with the up, down, left, or right arrows, and you try to avoid the eye for as long as possible. If you get captured, the game will end. All right, so now that we've seen a demo, now let's talk about how I use Q-Learning to find an optimal policy for the Runaway environment. So before we jump into the results, let's talk a little bit about what Q-Learning is. So Q-Learning is an off-policy, model-free TD control algorithm. Q-Learning works through iteratively updating the Q values for each state action pair from experience in the environment. And Q-Learning differs from other TD control algorithms in that it directly estimates Q star, or the optimal Q values, when updating the Q value for the previous state. Below is the update equation for Q-Learning. What this is basically saying is that when taking an action A at state S at time step T, observe the current Q value. Then update the Q value by adding the reward received from taking the action, plus the Q value of the best action state pair for the next state. This is why Q-Learning is an off-policy learning algorithm, because the behavior policy of which we take the action with is typically chosen by some epsilon greedy rule. However, the policy that we are using to update our Q value is always going to be absolute greedy. We're always taking the max. So that's a quick recap of what Q-Learning is. Let's look at the results of applying this technique to the Runaway environment. So I performed Q-Learning on the Runaway environment for 5,000 episodes. The agent's behavior policy was set to be a decaying epsilon greedy policy with a starting epsilon of 1, and the epsilon was decayed at a rate of 0.995 until it reached a minimum epsilon of 0.001 where it remained constant for the rest of training. The decay strategy was employed to balance the explore-exploit trade-off in the most efficient way possible. So at the beginning of training, I wanted the agent to learn as much as possible about the environment, and towards the end of training, when the estimates of the Q values were much better, exploit them to hopefully converge to an optimal solution. The plot shows the 50 episode moving average of the rewards over time, and convergence happened when the rewards hits consistently above 1250. And so we can see that at around 2000 episodes, the agent made a big breakthrough and ended up shooting up its average rewards to above that 1250 mark. We see that it converges relatively quickly. So now let's see this policy in action. So interestingly, from the agent's movements, we can see evidence of the epsilon greedy policy that we chose in the way that the agent moves sporadically around the screen. Additionally, since there's no incentive for the agent to move as far away from the minion as possible, the agent stays for the most part very close to the minion without getting caught. Also, as an implementational note, the agent is only caught if the centers collide, so that's why you're seeing the sprites overlap, but the game not ending. And note that near the end of the episode, the agent didn't get captured when it froze. Rather, the agent learned to exploit a bug in the way my minion moved by finding a state where the minion was fixed. And so the agent just collected the rewards without having to move, and the minion didn't catch it. So I need to go fix that bug, but I left it in here because I thought this was an interesting finding that my Q-Learning found a bug in my code. So some future directions for this project would be to train an agent to generalize to the minion spawning in other locations, and additionally having the minion adopt a stochastic policy where it makes a random move every once in a while. The fact that the agent and minion spawn in the exact same location every time at the start of the game with my current environment setup, and the environment moved in a my minion moved in a completely deterministic way, made this problem actually amenable to tabular Q-learning. However, to account for the random minion spawning and the stochastic minion policy, it would require a reasonable estimate for all Q values, which is a very extremely large and intractable state to keep track of in the tabular case. And it'd also just take a really long time to learn to estimate at all of those values. So to do that, it might be a good idea to choose some sort of Q value approximation approach to solve that type of problem. So another interesting experiment that would be very cool to try would be to change up the rewards framework to see how it influences the agent behavior. For example, changing the reward payout at every time step to be proportional to the distance to the minion rather than a constant payout as it's set up now would force the agent to learn to avoid the minion by being far apart rather than just avoiding the minion at any distance. In our case, it tended to stay pretty close. So that concludes this presentation. Thanks, Brian. Thanks for watching, and thank you, Brian, for making this class a really great capstone on the MSDS program. So also the code's available on my GitHub, and the link's there if you want to go check it out.